So the first part of understanding the rock form minerals is looking at the most common minerals on Earth's surface. Given that the two most common elements on our surface are oxygen and silicon, the most common minerals are all going to fall into a class called silicates, which contain a silicon dioxide tetrahedron in some sort of shape. Now, these typically form, and most minerals start out in one way, shape, or form as liquid hot magma. And starting with mantle rock, you have minerals that crystallize at high temperatures, like olivine and plagioclase feldspar. And then as the magma cools and migrates and gets lighter, minerals with lower freezing points start to crystallize out until you get to quartz, which actually has a fairly low melting point. Now, we classify these primary silicate minerals from mafic, which generally quote-unquote dark and high temperature, to felsic, which tend to have more silica. We'll explain why this is in subsequent slides. So this will review what we did in class. This showing how we have ionic bonds like sodium chloride, aka and the crazy cat lady, and covalent bonds like quartz, which is silicon dioxide, entirely covalent bonding. And these covalent bonds tend to resist erosion by water, whereas the ionic bonds tend to easily break down in the presence of water, the way and the crazy cat lady breaks down in the presence of Mickey Mouse. So the first silicate mineral is also in the oxide. It's called quartz, and it is one of the most common minerals near our surface, at least on the continents. It's clear, it's hard, resists weathering, but has a very low melting point. It's often found in association with feldspars. There's quite a bit of these all around the county, both potassium feldspars, which are pink, and plagioclase feldspars, which are often white, and you can see some stripes on the lower one that have, these are known as striations associated with the mineral structure. Now, if we take a look at the mineral structure, like quartz, feldspar has a network of silica pyramids or tetrahedra. But interspersed are some cations. These are, again, the cats that help sort of hold together the crystal structure. And in the weathering process, these will be separated, and you'll have free silica and cations dissolved. Now, sometimes the crystal structure, depending on the conditions, instead of forming a network, the silica tetrahedra, especially in the presence of aluminum, will form these broad sheets, leading us to the what are known as phyllosilicates or sheet silicates. Here, the sheets are held to one another by cations, but the sheets themselves are composed of parallel networks of aluminum oxide and silicon oxide. Now, the two primary rock-forming minerals that fall into this class are biotite and muscovite. Biotite being black, like you see in the lower corner, muscovite being used for windows before the Russians had access to glass. However, one other mineral that falls in this category that also avails itself to this sheety structure is clays. This is actually not a single mineral, but many different ones, typically formed during the weathering process. And it's partially because they have these high surface area and very low mass per surface area that these minerals stick so well that they can actually be used as a clothing dye in places like Hawaii. These are also a sheet silicate. Now, sometimes instead of a sheet, the silica, as you get more and more other elements present and higher temperatures, the role of the cations and anions starts to become more important because is these are holding things together at higher temperature. Those electrical charges, while a bit flimsy in the presence of water, are very effective in the presence of high heat. Thus, these chain silicates, when the tetrahedra are arranged in sort of long chains, either double chains or single chains, the cations play a more crucial role in holding things together at high temperatures. So the two major classes we have here are amphiboles, or hornblende, which are double chain silicates, and pyroxene, which is a single chain silicate. You may notice as we go deeper into the silicates and get smaller and get more and more other stuff that we're seeing darker minerals. By the time you're getting to pyroxene, you're starting to see a little bit of green in the coloring here. And indeed, green is the new black when you're thinking about silicate minerals and darkness. And indeed, when we finally get to a mineral where the silica network is each separated from each other and each individual tetrahedra is attached to other tetrahedra only by ionic bonds, you get your neosilicates. Think of Neo from the Matrix. And olivine is our sort of favorite specimen of this. A lot of it in the mantle, a little bit of it in the crust, and that sample in the upper right corner is from a meteorite. It's nickel and iron is the metallic looking portion of it, and olivine is most of the green crystals you're looking at. So you don't see a lot of this on their surface because it's held together by ionic bonding, which quickly breaks down in the presence of water. So you do get these green sand beaches in a few rare parts of the world, but they do not last.